Hello everybody, and this is going to be the start of the Abstract Algebra lecture series. So, the way essentially this is going to go is I'm going to start with groups and then go to rings and then fields. And those are essentially going to be the big chapters. And then I'm going to also cover some stuff on modules and vector spaces. So basically we're just going to touch grounds on all the important algebraic structures. I won't have, or not that I won't have, but I don't want to spend a lot of time covering examples because I feel like those are best sort of read or, it's best to work with examples yourself rather than see other people work with examples um, because it's not as enlightening. And of course, the same goes with all of mathematics. It's best you do it yourself. Um, but lectures can be good to have an idea of, what to study. Um, so my lectures are essentially going to be following the book Undergraduate Algebra by oops, by Sir Lang. I don't exactly know how to say his first name. Um, And this is a wonderful book. This is the book that I use to learn abstract algebra. Um, it goes pretty in depth, especially if you do all the exercises. A lot of topics, not really topics, but especially like examples and some side things are covered in the exercises. So it's really good that you do all the exercises. Some exercises are used later in the text, and there's some very important things covered there. And I'm not going to cover all that's in the exercises, or really not much of it at all. I'm not even going to cover all the main material. Um, I really just intend to give sort of a glance at what abstract algebra is. So I will give that warning. There's a lot I'm going to be excluding, and I feel kind of bad about it, but I don't A, I don't like making videos too long, and B, I don't like making too many videos on, one series. So, without further ado, we're just going to get started with what the definition of a group is. So, a group is a set G along with an operation um, i.e. a map. This is just a function from G times G to G, right? So it takes into functions, or sorry, two elements of G, and it spits out another one. And these two things satisfy the following properties. The first is that this operation, which we typically call multiplication, is associative, right? So x times y times z is the same thing as x times y times z for all x, y, z in the group. So that's the first one. So this is associativity. The second one is that there is an identity, which in general we denote by E. In some contexts it can be 1, in some contexts it can be 0. It just depends on the context, but in general it's E. Interesting fact, this actually comes from a German word, I think, for unit element. I don't know what the German word is off the top of my head. I don't know German, but I found that out the other day. And so this identity satisfies e times x is the same thing as x times e is equal to x for all x and g. And the third property is that for all x and g, there is a y and g such that x times y equals y times x equals e. And so we denote y equal x inverse. Okay. So to recap, right, a group is a set with an operation, meaning I can take two elements of the group and get another one out. The operation is associative. The group has an identity element, meaning that the operation with the identity element fixes any other group element. And finally, there are inverses, meaning I can find, for any element in G, I can find another element which, when I take the operation on those two elements, I get the identity. So notice that x times y may not be equal to y times x in general. If x times y equals y times x for all x, y in G, we say G is abelian or commutative. And also in most abelian scenarios, we use plus instead of the sort of multiplicative notation, 0 instead of e, and negative x instead of x inverse. Okay. So that's what an abelian group is. So now what we're going to do is prove some fairly basic things about groups, just with our definition. The first thing is that the identity is unique. In other words, there is only one identity element. And the proof of this is very simple. It's just one line. Suppose E and E prime are two identities. Then E is equal to E times E prime, right? Because E prime is an identity, so multiplying by E prime doesn't change E. But E is an identity, so multiplying E prime by E is equal to E prime. And so we've proved that the two identity elements have to be equal to each other. The next proposition is fairly straightforward as well, and that is inverses are unique. So again, what we do is suppose y and z are inverses of x, then y is equal to, right, e times y, and e is equal to z times x, right, because x and z are inverses. Now I can swap the parentheses here because our operation is associative. So this is z times x times y. X and y are inverses, so x times y is e, and then z times e is z. Okay, so we've proved that the two inverses of x are equal. Now I'm going to give some examples of groups that you've seen before and maybe not realize that they were groups. So some big examples are these sets, like the integers, the rational numbers, real numbers, and the complex numbers with addition. And since we're using addition, of course this isn't always the case, but you should train your eye to see if you're using addition, then it's probably going to be an abelian group. Okay, so in the simplest case, right, the integers, right, under addition, right, if I add two integers, I get an integer. Okay, addition is associative. There is an identity, namely 0, right? If I add 0 to any integer, I get that integer. And there are inverses, namely the negatives, the negative integers, right? 1 and -1 are inverses because they add to 0. Notice, for instance, the natural numbers, sometimes defined with 0, sometimes not. I'm just going to define it without 0 for this case, but it doesn't matter either way. Is not a group under addition because there are, 1, there's no identity, 2, there's no inverses, right? Even if we added 0, right, 0 would be the identity, but there's still no inverses. Some other examples, if we take the rationals minus 0, reals minus 0, and the complex numbers minus 0 with typical multiplication. And even though they are multiplicative, or we write them with multiplication, they are also abelian. Right? Because it doesn't matter, right? In rationals, real numbers, complex numbers, multiplication is commutative. It doesn't actually matter the order. And of course we use multiplication here to distinguish from addition, right? We could still add these rational, real, complex numbers, but it wouldn't be a group in this case because we take away 0, right? That's the additive identity, so it can't be a group under addition. Other examples are Q plus and R plus with multiplication. So here, right, Q plus and R plus is the set of X and R with X being greater than 0. Okay. And the same thing with the these are just positive rationals and positive real numbers. Okay, so these are all like very familiar examples that you've seen. Some other examples, there is the trivial group, which is the smallest group you can construct. It just contains an identity element. The operation, well, it doesn't really matter what the operation is, because there's only one function from g times g to g, right? It just has to send e times e, or the ordered pair e to e, right? And that automatically gives you your associative operation. There's an identity, and every element has an inverse, because the only element is the identity, and its inverse is itself. So that's why it's called a trivial group. It sort of satisfies all the group axioms in a very simple manner. There's also some other small things, right? So 1 and -1 with times, right? With multiplication. This is billion. Okay, so 1 times 1 is 1, -1 times -1 is 1, and 1 times -1 is -1. Similarly, there is the group 1i, -1, and -I, where I is the complex square root of -1, right? So I times I is -1. You can check sort of. The first thing you have to do is check that that the multiplication actually keeps you inside the group, right? And here that's the case, right? Of course, 1 times everything's going to be in the group. I times all these things is going to give me other group elements, and so on and so forth, right? If I took out -1 and it was just 1i and -I, then it would no longer be a group. And there's going to be lots more to come, although there are very important examples I won't cover in the interests of time. Okay, and so those are all the examples, and now I just want to wrap up this video with some more basic definitions. Okay. So the first one is the direct product. If G and G prime are groups, then I can make the Cartesian product G times G prime is a group with operation. So the way I multiply elements of this set is if I take two elements, which are of course ordered pairs of elements in the groups, the way I multiply these two ordered pairs is by multiplying pairwise, right? And so I'm abusing notation a little. I'm using the same, notice that I'm using the same symbol for all these group multiplications. They may not be the same operation, right? But I'm just abusing notation. And actually later on, I'm going to drop the dot entirely. So I guess I'll write that down. Later on, instead of writing x dot y, I'm just going to write xy. And it will be implicit multiplication. And the final definition that I'm going to give for this lecture is a subgroup. So if H is a subset of G and 1 x times y is in H for all x, y, and H. 2 E is in H, and 3 x inverse is in H for all x in H. Then H is a subgroup of G. And for the sake of just writing, I'm going to use this notation that I don't think I've ever seen, but I'm just going to use it as a sort of just handwriting shortcut. If I have this G next to a subset symbol, that's going to mean H is a subgroup of G. Just so I don't have to say it. This also will, if I haven't already defined G to be a group, this will also automatically define G as a group. So it just saves a lot of writing time. Of course, I don't want to bog down video time with writing. Later on, we'll see something called a normal subgroup, and normal subgroups actually have their own notation. But just the case of general subgroups, I don't think I've ever seen a specific notation for it, so I just want to use this notation. And I guess one last thing to say is that any group has at least 2 subgroups. Namely, the trivial group is always a subgroup, and G, or the group itself, is also a subgroup. So anyway, that's it for the first video, and I hope to see you in the next one.